right, welcome everybody to the second installment of AMS Colloquium for the fall 2016 semester. Very excited that you all are here for Professor Art Owen's talk and also for our second installment of AMS Colloquium Correspondence. So we'll start off, I'm your host, Paul Constantine, Assistant Professor in the department. We'll start off with Grace Hallbach talking about primes. Blue dots.
Okay, so the first thing I have is actually this visualization, which doesn't just show primes, it shows all numbers. So primes have a lot of interesting features, one of which is the assumption that they behave like random numbers. So American scientist writer Brian Hayes looked at the remainder of the first million primes divided by 7 and noted that the result is a sequence of integers drawn from the set 1, 2, 3, 4, 5, and 6 that looks like the outcome of repeatedly rolling a fair die. However, each roll of the die is independent, and now there's some evidence that primes might not be. So Stanford mathematicians Kinjal, Stolarsky, and Robert Limpa Oliver provided theoretical and numerical evidence that the last digit of consecutive primes is subject to a bias, which is that prime numbers repel potential primes with the same final digit. For example, in the first billion prime numbers, a prime ending in 9 is about 65% more likely to be followed by a prime ending in 1 than another prime ending in 9. So when Hayes read the article, he started creating heat maps for consecutive primes. So this is one of them. As you can see, there's a cold region where the ending of a prime ending in 1 is followed by another prime ending in 1, and there are heat regions as well. So as mathematicians yourselves, you might be wondering if this pattern only exists in base 10. That's not the case.
Yes, that's what I was wondering.
I know you so well. Stolarsky and Oliver also considered this and found that the bias persists in other bases. And Hayes also has the models with different bases. So here's one with the mod 13, and you can see the cold region again in the middle. And this one is base 17, where you can see another cold region in the middle. Why is this interesting? It provides some evidence for the twin primes theory, which is that there are infinitely many prime pairs that are only 2 numbers apart. Additionally, prime numbers are an old topic, so it's always really cool when something new is discovered about them. To understand the numerical evidence for the study, you really only need to know what prime numbers are, and the theoretical evidence is based on the Hardy-Littlewood conjectures, so you need a stronger background in number theory to understand that. And since the math department at Mines is more focused on applied research and applications than number theory, there isn't any research being done on campus that deals with this. That's it.
Thank you, Grace, for telling us about primes. Where did Jaden go? Did Jaden leave?
I'm in the back.
Okay. Jaden, we've got a seat for you right up front. Yep, right here.
Yeah.
What?
All right, let's thank Grace one more time. Second installment of Colloquium Correspondence. Up next we have Izzy Aguiar and Jessica Daters, who are going to give us a profile of Professor Paul Martin. Here is this.
Remember the rival role.
Gotcha. All right, so I'm Jessica.
I'm Izzy. We're both seniors in math.
And as we went into this week trying to figure out which professor to interview next, we found this little blurb on the AMS website that said that Dr. Martin was the new editor of the Princeton Companion to Applied Mathematics, to which he also contributed 16 articles. We thought, that's pretty interesting, kind of a big deal.
And as this next slide will show you, this is not the only accomplishment that Dr. Martin has done in his life. There are also all of these. We're only going to have time to talk about 3 of them. But one of the most surprising and great things we learned while we were doing this presentation, or the research for it, is that all of these things that Dr. Martin has done, we've never really heard about them before, and it's really a testament to how humble he is as a mathematician and a professor. So,
Dr. Martin got his master's and PhD at the University of Manchester, where he then went on to have a full-time position as a professor. He actually won the Fulbright Award twice to take 2 sabbaticals to the US. We actually didn't know this fun fact until we looked on his website. But one of these sabbaticals was to the Colorado School of Mines, and then eventually after the designated waiting period, which is designated by the immigration laws, it's also fun if you ever want to look into it, he received a full-time offer to come to Mines, where we hope he will stay forever.
Forever?
No pressure.
So like we were saying earlier, the reason why we were interested in digging deeper in Dr. Martin's life is because we found out that he is one of the associate editors for the Princeton Companion for Applied Math. But Jessica, what is the Princeton Companion for Applied Math?
You know, Izzy, that's a great question. So, the Princeton Companion to Applied Math is actually designed for undergraduates.
Like me?
Like you! So it's actually designed to be accessible to people with an undergraduate understanding of mathematics, which is a real testament to the authors that the editors have commissioned to write these articles, because they're able to not only be experts in their field, but be able to communicate that information at a level that people who don't have that high level of understanding can understand.
In case you were wondering, Dr. Harriman and Dr. Constantine both have articles in the Princeton Companion, and like Jessica was saying, it shows that they are experts in their fields, but also experts at communicating.
And you know, Izzy, it's actually a beautiful book. So if you're ever interested, like you need some nighttime reading material,
What are you doing tonight?
Do you want to go pick it up?
Yeah.
I hear it's pretty affordable too. Anyways.
So one of the biggest things we think that no one talks about is that Dr. Martin is the editor-in-chief of the Siam Journal for Applied Mathematics.
So this is kind of a really big deal. So this isn't just like some little journal off in a corner of a corner of a corner. This is the journal, the Siam Journal of Applied Mathematics.
Yeah. It's a huge deal. Dr. Martin gets 500 papers to his desk every year that he has to determine whether or not they're qualified for being in the journal. And what are the criteria for being in the Siam Journal for Applied Math?
Well, Dr. Martin looks for articles that not only use interesting mathematics, but also have interesting applications. And so I think as people who have done projects or research in mathematics, we can all appreciate how difficult it is to operate in that intersection.
Yeah, we can. So the takeaway that we want you guys to have from this presentation is that you never know the amazing things your professor or colleague has accomplished until you've asked. Thank you.
That was fantastic. One more time for Jessica and Izzy. Really good. Now it is my pleasure to introduce Professor Art Owen from the Statistics Department at Stanford, and he and I are going to have a short chat at a lovely autumn lane. So, Professor Owen, and we have this gift for you from our department. You can open it if you want. It includes a notebook with the department logo and a pen, so you can take us home and always remember us.
Oh, but even better.
And a mug.
Okay. That's the problem.
That's the important one.
Yeah, that's what we're looking for.
Helps get the work done. Professor Owen, thank you for joining us at the AMS Colloquium today. You're a professor of statistics at Stanford. You did your master's and your PhD at Stanford, and then you've been there since as a professor. As we all know, Stanford Statistics Department has been sort of at the forefront of using computational tools for statistics. So what is your favorite moment in the history of the Stanford Statistics Department?
Well, getting the new building was nice.
Okay. You have a building that is all statistics.
We have a statistics building, and we used to have a statistics building, and it was the second oldest cinder block building in the state of California, and considered to have no historical interest whatsoever. So it got knocked down, and we got a brand new building.
Sequoia Hall.
And the new one's called Sequoia Hall.
Great. So according to your CV, which on your website was last updated January of 2015, you have 2 books, 80 journal publications, and several other articles since 1984. Which of those is your favorite and why?
Oh, man. Well, I kind of have 2 favorite-y things. So empirical likelihood is something I'm pretty known for, and it lets you kind of have it both ways. Maybe you want a likelihood, but you don't want to have to say what a parametric model is. And so you can kind of have it both ways. And then the other thing, having it both ways, I did some work on randomized quasi-Monte Carlo. So quasi-Monte Carlo, you space the points out evenly instead of just random Monte Carlo sampling, and you get higher accuracy. But because it's not random, you don't get an estimate of your error. And so I did this trick of randomizing within the quasi-Monte Carlo family so that you could repeat it and estimate error. And then it turned out to actually reduce the error by some cancellation stuff, which is sort of a surprise. So those are my 2 favorites.
And you're still working on these today?
Still on those today.
Yeah. And in fact, we just had the Monte Carlo, quasi-Monte Carlo conference at Stanford that you organized. How many participants?
We had about 220 or so registered.
Yeah, it's a great meeting. If anyone's interested in Monte Carlo, quasi-Monte Carlo, we should talk afterwards.
And next one's in Rennes in France in 2018.
So you have also had a lot of interaction through consulting and sabbaticals with industry, including Genentech and Google, Bell Labs. How would you contrast academic statistics with industrial statistics?
Oh. So I kind of like to have a hand or a foot in both sides. And my undergraduate degree was a co-op degree where I'd spent 4 months in a university and then I'd spent 4 months in industry. And I was kind of ready to go back to the other one after each of those each time. And so now that I'm like in the university world, I really like going on sabbatical to industry, like Genentech or Google or Bell Labs, where the people own the problem. And then you try your hardest to do something for them. And then sometime later you think about, well, what mathematical methods or statistical methods were missing that I wished existed, and then you work on them after. So I like the alternation. I don't think I'd be happy just stuck on one side of that fence.
And you think one gives motivation to the other and vice versa?
Yeah, definitely. I think for statistics anyway, you really want to, well, if your statistics are not anchored in some mathematics, they could just dry up and blow away. Like it can just be a whole series of tweaks on tweaks. So there needs to be some math. But if it's not motivated by something that people are really trying to do, then it's also unlikely to have permanent value.
So one last question. What do you do other than statistics?
Oh, well, okay, so I spent a lot of time with my family, and of course now my kids have graduated and left the nest. I barbecue a lot, I ski, a little bit of travel, stuff like that.
Like to visit us here?
Yeah, this is a kick, yeah.
And you're going to see a little bit of Colorado while you're here also?
I did, so I actually saw it already, so I got to Denver on Wednesday, then Boulder yesterday, and I'm going to go to Red Rocks because I've always wanted to see a concert at Red Rocks. And
what are you going to see?
It was some group I'd never heard of before, but I
Okay.
sampled them online and they sounded good, so
All right.
it's some kind of modern thing.
Okay. Modern music at Red Rocks.
It sounded good, so that's my standard for music.
All right.
Yeah.
Great. Okay, well, now Professor Owen is going to give us a presentation on permutation p-value approximation through the generalized Stolarsky invariance.
Okay, well, thank you, Paul. It's really a kick to be here. I've never had this kind of experience with,
This.
there you go. With the colloquium before. Okay,
Nor has anyone.
okay, so here are my 3 co-authors, and they all graduated in June. The 2 on the left were working with me. I had a 3rd student who also graduated, but she did something else. So Hera was working on gene set analysis, and Kinjal was working on quasi-Monte Carlo, but not in the cube. Most of quasi-Monte Carlo takes place in the cube. And it turned out I should have a big intersection sign here because their two topics intersected in what I'm going to tell you about today. And then we also had some help from Qingyuan, who's mainly been working on causal inference, but on a lot of other things. And Paul, what should I aim for in terms of?
350 to 355.
Okay, and there's a clock up there. Good.
Yep.
Okay. Okay, so I'm going to talk a little bit about permutation testing. And it's a popular thing in biology or bioinformatics to use permutations. They have some kind of face value validity. And it leads to something in mathematics called the Stolarsky invariance principle. And it was surprising to me that Stolarsky popped out of gene set testing. And what we'll talk about is actually the opposite of quasi-Monte Carlo. So quasi-Monte Carlo is all about approximating a continuous number, like an integral, by something discrete, like a sum. And this problem is different. Here the discrete answer is actually the right answer, and the continuous one is the approximation. Okay, so we'll extend some very nice work by Rauschart and Dick, and then we have a probabilistic derivation of Stolarsky's invariance principle. So it's been out for about 40 years, and it was a fairly complicated thing that Stolarsky proved, and Rauschart and Dick simplified it using reproducing kernel Hilbert spaces, and we think it just comes down to a page or two of probability. Okay, so then we think also that we have an even better way to approximate permutation tests. Okay, so let's just say what a permutation test is. Not everybody here will be a statistician, so what do we have? Well, as is common in statistics, we have an x and a y. Okay, so maybe there are n people, and we have x, y. We measured x and y on them both, and we're wondering if there's any association between the x that we measure and the y that we measure. And so you might have some way to measure t that just measures whether x and y go together. A correlation would be the simplest one, or an r squared, but there's lots of other things that you might have. And if you take a random permutation of the numbers 1 to n, or just put them in any arbitrary reordering, then your x turns into x sub pi, and it has elements x pi I, where pi I is the ith permutation. And in a permutation p-value, what you do is you do all n factorial permutations of the x matrix, and you work out your association measure all n factorial times, and then you count how many times it was more than what you got in the data. And if it's only more than what you saw, like 1 time in 1,000, then you think what you saw was a real association and it was not random chance. Maybe 1 in 1,000 isn't good enough for your problem, or maybe you need 1 in 1,000,000. But there's some small number epsilon that you want to beat. Okay. So that's a p-value, and it's actually an exact p-value. So most of the time in statistics, we don't have anything exact. Or you make an assumption that the data were normal, but of course they weren't. So then you have an approximation. Okay, permutations can give you exact tests. So that's pretty sweet. And there's some deep group, not that deep, there's a couple lines of group theory. Most people that use permutation tests have completely forgotten the group theory if they ever knew it. Okay, so you can present it purely based on intuition, but if you like to see the math, it's group theory inside. Problem is it's expensive to compute that. N factorial could be a lot of computation. Okay, so what do people usually do? They don't usually do all N factorial. What they'll do instead is they'll, take a random sample. There's an intermediate thing here. Sometimes if y only takes 2 values, like 0 and 1, and you swap 2 people that had zeros. If you swap zeros, you didn't change anything. So there's only this many distinct permutations that matter. Say the total number of observations choose the number of zeros. That could still be a big number though. You might have 100 choose 50. That's a lot of work. You don't want to do them all. So what people do is Monte Carlo sampling. They'll take m random permutations of the data and see if it got bigger than the real one. And then the fraction bigger is the p-value. And you always should, not everybody does, but you always should add a 1 for the original data you got in the numerator and the denominator. If you don't do that, you might get a p-value of 0. which says that what you saw never happens, but wait, I just saw it. How can you tell me it never happens if I just saw one? Right? So you really, it's malpractice if you're not adding the 1 to the top of the line. So always do that. Of course, it means you can't get a p-value smaller than 1 over m that way. So your true p-value is always bigger than 1 over this big N, which might be n factorial or that. If you did it by Monte Carlo, you'll never get a p-value smaller than 1 over m. When you test thousands and thousands of gene sets, a lot of them might end up having the same exact 1 over m, and then you don't know which one's the most interesting because there's a bunch of them tied in the lead. So this granularity is kind of a nuisance. Okay. Now, suppose you need a really small p-value. You're not going to call it a discovery unless your p-value is smaller than epsilon. Well, then your number of permutations has to be more than 1 over epsilon, at minimum. And there's a rule of thumb that says, well, it should be more than 10 over epsilon. And I did some work with Jessica Larson to turn that into a power statement, just because some referee really hassled us over. The referee just didn't agree with this paper. It gave us all kinds of trouble. But anyway, in a genome-wide association test, what they'll do is they'll look at every gene in a genome and see are any of them that they can measure, any of the ones that vary, they really differ, like with diabetes or not diabetes. Or Parkinson's was the one that I looked at with Jessica Larson, who was at Genentech at the time. Well, the standard of evidence there is your p-value should be smaller than 5 times 10 to the minus 8. So then you have to do a lot of permutations to get there. So then what we're trying to do is cut corners. Can you get the permutation p-value without doing all those permutations? So the context was gene set tests. So we get for this gene in that person, we get a number. Could be expression, could be a SNP. And then there's a 0 or 1. And 1 might be like, does the person have Parkinson's or not? And then a gene that's linked to Parkinson's or a gene set that's linked to Parkinson's, it's not really proof of that much, but you follow up. Okay, so it's an association. It might be causal, it might not be causal, it might just be junk, but you fish where you find something. Okay, so it could be that these genes are causing the disease, or it could be X might actually be a treatment, and it's making some genes respond. Now, the biologists don't like to just work with the genes one at a time. It's more reasonable for them to think of, like, maybe there's 80 genes that operate together in some biological pathway. And if that whole pathway is linked to your disease, then they kind of understand what they're getting, because maybe they studied that pathway. So one reason is they can interpret better a gene set than a gene. The other thing is, you might have weak evidence in each gene, but if you combine that weak evidence over 80 genes, the combination might be much more convincing and compelling. So this is why the tests that people want to do are on sets of genes. So it's that set of genes linked to Parkinson's. And of course, there are lots and lots and lots of sets of genes. We know there's more sets of genes than there are genes, right? It has to be. There's maybe several thousand that are known in gene sets that are known and studied. Okay. Well, how are you going to tell whether some disease is associated with a set of 80 different genes? Well, it turns out there's a lot of ways to do that. And it's kind of gone in a Rube Goldberg way. All kinds of really obscure, complicated, tricky, something that seemed like a good idea at the time. There's a lot of stuff that's been tried to figure that out. Ackerman and Strimmer did an extensive simulation, and they tried 261 different ways to test whether gene sets were relevant. And they found 2 clear winners. And the winners were really simple, so Goldberg didn't win. Okay, so here are the winners. So first of all, we'll make the x and y have mean 0 and make the unit vectors with mean 0. And then we'll do a correlation between X, say the disease, and the Y and gene G. Or we could do a T statistic, which is pretty much the correlation. And the winners were, go to your set of genes and add up all the T statistics. Or go to your set of genes and add up all the correlations. It's not that different. So that's one family of winning methods. The other family of winning methods is, well, square them and then add them up. So why would you, if all of the genes move in the same direction as you go from healthy to Parkinson's, this will pick it up. If some of them go up and some of them go down, this will catch it. Okay, these are pretty simple-minded things. And then if you want to get a p-value for it, you can't use the, it's not easy to use the regular stuff because all those genes in the gene set are highly correlated or somewhat correlated. And so that's where permutation tests come in. And permutation tests really appeal to biologists. They really understand that if you take the labels, who got the disease and who didn't, and shuffle them around, that passes all the sanity checks. It seems reasonable, like gives face value validity. Okay, so just add up the T statistics or their squares. And you probably won't do better than that. And why is adding up the, we just ended up adding up the correlations. And the T statistic, if you do a Taylor expansion, the T statistic is pretty much the correlation, a multiple of the correlation plus the correlation cubed. And we're interested in the case where it's a lot of little small correlations, so the cube just doesn't matter. Okay, so then, for that linear statistic, if you add up X transpose Y, G, you're just adding up X transpose times the sum. So all you need to do is test whether a linear correlation is significant. The quadratic case is a lot more complicated, and Hera's dissertation looked at that. Okay, so how are we going to approximate the permutation test? There's some classical methods called saddle point approximations we compared to. There's a very old method where people just try the method of moments. If they don't quite get the job done, there's maybe not enough theory, or they can be numerically problematic. Some of these methods will fail to compute what you want. Okay, so we take our X, which is a 1 if you have Parkinson's and a 0 if you didn't. We subtract the mean, which is the fraction of people with Parkinson's, and we divide by a standard error. Now we have a point in the unit cube. Our gene score is also, unit sphere. Our gene score is also a point in the unit sphere. Okay, so it's just on the surface of a sphere. Okay, Z transpose Z is 1, and the dimension is n minus 1. Actually, we're on a subsphere though, because we made all the things have a mean 0. We centered them first. So that just knocks the dimension of the sphere down by 1. We're working on the equator of a high dimensional sphere. And so we're just 1 dimension less. Okay, so X and Y are both points in that sphere. The permutation p-value, well, all we'll do is we'll permute the X all these possible ways, and count how many times we beat the thing that we saw in the real data. Okay, well, if our X and Y are really, really close, then it means we're in some kind of a spherical cap. So there's Y, and then X would be on this part of the spherical cap here, and anything that's in the cap gives you a bigger dot product than what we saw. So it's going to be geometry now. Okay, so here's our p-value. It's what fraction of these permuted points beat the original data, which is just what fraction of the x's are in a spherical cap centered at y. Or what fraction of the time is y in a spherical cap centered at x, because it's completely symmetric. If I'm in your cap, then you're in my cap. Okay, so there's a symmetry. Well, the first approximation you could come up with is just take the volume of that spherical cap and divide by the volume of the sphere. If each spherical cap is getting its fair share of the points, then the volume should come out about right. Okay, it's actually not a great approximation, but that's why it's like our first approximation. And if you did a normal theory t-test, this is what you'd actually be getting. But it's not that great. We'll get a better approximation later. Okay, so here's our geometry. So there's Y, the gene set, the gene value. There's X, it says who got Parkinson's and who didn't have Parkinson's. And they're pretty close. Okay, so maybe that gene set is involved with Parkinson's because it's close. And then these open dots are what happened if you take this X vector and you start permuting. So you swap a Parkinson with a non-Parkinson and moves to here, you do another swap there. If you look at all of the possible swaps, you get all of these dots. So these are all the permutations. And now, here's a spherical cap centered at the Parkinson vector, at the gene vector. And our p-value is how many of these circles are in the red cap divided by the total number of circles. And our estimate is the volume of the cap divided by the volume. Okay, so here's what here's the answer, p, and here's our approximation, p hat. And so our error is the square. You say, well, how bad is our p-value? It's that squared error. And then we can average over all of the gene sets on the unit sphere, and then we can average over all of the t statistics, go from all of the radii of that spherical cap, going from -1 to +1. So this is a measure of the average quality of that p-value approximation over every possible spherical cap you could have. And so the true p-value is just this fraction of points, and p hat is the volume of the cap. And this is the uniform distribution on the sphere. Okay, so that would be a discrepancy, and the quasi-Monte Carlo people study discrepancies all the time. But it's actually not that good for us. We really only care about small p-values. If the true p-value is close to 60%, we don't actually care. We just know that's not an interesting gene. If the p-value is down around 0.001 or less, then it might be interesting. So we only care about the small ones. So we'll have to come back to that later. How do we do the small ones? Okay, so here is Stolarsky's invariance principle from 1973. So Stolarsky says, let's integrate all of these squares. The true p-value minus the approximation. And his points could be any points. They don't have to be from the permutation set. And up to a constant, it's this difference. You take the average distance between 2 points on the sphere and subtract the average distance between 2 points in your point set. That's really strange. Like, this seems like really complicated. I've got spherical caps, and I've got combinatorics and counts going on. And here I've just got geometry. Here I've got L2, and here I've got L1. How come I have an L2 left-hand side and an L1 right-hand side? Well, maybe there's an integration by parts. Maybe there's other people that get that. But it's a very puzzling, it's puzzling to me that this, on the face of it, that could actually happen. And then this just comes from the surface measures. Okay.
So the integral to go bigger, right? More dimensions.
It has to be bigger, yeah. So if you find any measure on the unit sphere, it will always have a smaller double integral than the uniform measure on the unit sphere. And the only reason this guy loses is because you count the diagonal where k equals L. So he's going to have some zeros. Okay, so there's something in statistics called the energy distance. This is actually up to a constant, the energy distance between the uniform distribution on the sphere and the uniform distribution on the points. Okay, so using Browshard and Dick, we do a weighted Stolarsky. So we put a little weight function and only look at spheres of the size we want. And if you put this weight function in, then the right-hand side of Stolarsky turns into something involving a reproducing kernel from a Hilbert space. And so the weight goes in, the kernel comes out, and here's the kernel you get. And what we're going to do is we're going to take this weight and we're going to make it only go where we're really interested. So if we're interested in a correlation of 0.4 or a height of 0.4, we'll make a little measure that's very small and positive. It spikes right where we care, and then it goes flat. And then we'll just let those epsilons go to 0. And if we do that, chug, 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 take the limit as those 2 epsilons go to 0, we get the accuracy of this volume, but only over p spherical caps of exactly the size that we observed. Okay, so then it's tuned more closely to what we wanted. Okay, and then we get this result. So here's the root mean square. Here's a mean square error over p-values of exactly the size we care about. We need the volume of the intersection of two spherical caps, and this volume is the chance that is that the point y lands, or that a point lands close to both x and y. So this is the probability of two things happening, and that's the average probability of one thing happening. So it ends up, there's a probability argument that will get you that thing too. Okay. So what we'll do is we'll let the permutation point could either be in the spherical cap or not, and this p-value, the true p-value is just the fraction of points in that cap, and we get a mean and a variance as we move the cap around. This p-value that we get, the naive p-value, is just the average of this one as the point y floats around uniformly. What's the volume of a spherical cap? Well, it comes from the incomplete beta function. What's the volume of the intersection of two spherical caps? It's kind of gory, but it's just, you just get the volume and then you integrate out. So it's, it's just shenanigans for special functions. You look at it in the privacy of your office. Okay, so how are we going to calculate that variance? Well, x is all zeros and ones. So by the time that you put it on the unit sphere, it's all alphas and betas, where the alphas are negative, the betas are positive, and they sum to 0, they sum squared to 1. The important thing is, if you have two of these points, how many swaps are there? Like how many, if I gave you another point like this, how many ones would be in a place that used to be 0, and vice versa? These permutation points form a lattice, and we would love to bound the number of points in a given volume, and we were not able to do it using the geometry of numbers. I should probably skip some stuff. Okay, if I have two of these points, then, and I tell you how many swaps you had to make, then you can tell me what their dot product is. And then if I want the variance of that approximate p-value, it's a sum like this. And the important thing is we only have to consider swaps. So we only have to do an amount of work that grows like, say, either the number of people that don't have Parkinson's or the number of people that do. We don't have to do any n factorial or n choose anything stuff. So it's a fast computation. Okay. Now I want to tell you the thing that I think is better and I'm actually more excited about, and I think you should maybe really use. So now, instead of taking every spherical cap on the whole sphere of our volume, we're going to nail one of those, basically we're going to nail it down to this point x0. And so we'll only look at spherical caps with exactly the volume we want, and where their center is as far from x0 as the real data center was from x0. So here's the real gene vector, dot producted with Parkinson. And then we're going to only look at other ones at the same distance from the Parkinson variable. And so geometrically, this is the thing that tells you who has Parkinson. This is the gene. Here's our spherical cap that we want. And what we'll do, let's see. Okay. So now, this blue curve tells you every value of y that's the same distance from the Parkinson variable as our original one. And we're only going to consider red spherical caps whose center lies on this blue curve. And so here are all of these spherical caps. They have the same volume as the original one, and they're the same exact distance from Parkinson's disease. And so what we'll do is we'll get, for all of these spherical caps, we can figure out how many points do they have in them and get the mean and the variance. And the mean over all those red caps will be our new estimate. And then the variance we'll find is actually pretty small. we really want the soup. We really want to find which of those circles has the most points. But we're only going to be able to do L2. We can't do L infinity. Maybe you guys can do that. Anyway, we can only get the L2. There are two ways to go. You can just grind it out. You can just grind it out with probability theory, or you can grind it out with reproducing kernel Hilbert spaces, and you get the same exact answer both ways. I'll give you a hint about the second way. Just the first line is most important. Here is the error between the volume and the p-value, and the p-value approximation. And before, we specialized to only consider p-values, only consider spherical caps of the same diameter as the original. Now we're going to make sure that they only have the same distance from the Parkinson vector as the original. So we put a weight function here like we had before, and a weight function there. Weight functions go in, and reproducing kernels come out. And then we just take a limit as this goes to a point mass. And this guy was already a point mass. And so that's what we do, and then we get something that we can compute. And we can compute it reasonably quickly. You don't have to do millions of permutations. Okay.
So, is there a way to interpret this as importance sampling?
Ha! I wish. It's sort of. So in Hera's dissertation, the quadratic problem is much, much harder because a quadratic spherical cap is a lot less tractable thing to deal with. And she looks at importance sampling in order to get there. At this point, maybe it's like an extreme kind of importance sampling because you have a measure where you drop the dimension down by one or two things. You made the cap exactly the same. You made the distance from Parkinson exactly the same. So it's okay. So p hat 1, that's where you just take the volume. That's what you would get if you did a t-test. Okay, so it's just the volume of the spherical cap. And we're going to have equal numbers in the two groups. So 5 healthy, 5 diseased, etc., different numbers. And we tried unequal, it didn't really make much difference. And then if you make the, and then what's the, p hat 1 is the volume of that spherical cap. So we'll make the volume of that spherical cap go down to like 10 to the minus 10, 20, 30. So really small p-values. And then here's the log 10 of the root mean squared error that comes out of Stolarsky. So if the true p-value was 10 to the minus 10, the root mean squared error might be as high as, 10 to the minus 7 or something. That's pretty bad. Well, that's with 5 of each. If you get larger samples, it's a bit more accurate. But still, if you tell me that the number is 10 to the minus 30, but the accuracy, the error is 10 to the minus 20, that doesn't feel very good. Basically, if you want a conservative bound, you would just take this as your bound. You'd say, I'll add 2 or 3 or 10 standard errors or whatever. And the fact that the estimate was way below would do you no good. That's why this is not that good. These error estimates are way bigger than the thing you're trying to estimate. But that second one I showed you, p hat 2, where your circle rolls around and it always stays at the same distance from Parkinson, that one has a relative error that's pretty much equal to the estimate. So you get a p-value of 10 to the minus 40 and an uncertainty of about, well, maybe 10 to the minus 40. I have a hunch that that the L infinity distance is also pretty small. I think there can't really be any big numbers on that circle. If the mean is 10 to the minus 40 and the standard deviation is 10 to the minus 40, you can't get stuff that's much bigger than that. And I think it would be nice to get a better mathematical handle, a better bound. I would love an L infinity, but we don't have L infinity. Okay, so that 45-degree line I thought was pretty salient. And here it bumps up, so it's way over. I mean, it's a log scale, but the biologists really don't mind. If you tell them it's 10 to the minus. Pardon me?
Maybe 1 order of magnitude.
Yeah, the one actually you're pretty good eye. It's about like a and then if you told somebody that there's a 10 to the minus 50 chance this could happen, you say, oh no, sorry, it's 10 to the minus 49. It's not like you're changing their scientific conclusion that much. So that's actually okay. Also, the root mean squared error in that approximation actually drops to 0 once the p-value is below 2 over n, because there's actually nothing closer than that one closest point. The second closest point is 2 over n away. And so you get the exact answer. Right here, these lines actually, they really do go down to minus infinity error. Okay, another coefficient of variation, you called it. It was an order of magnitude. The most we see is about 10. So this is the standard deviation divided by the estimate, and you see it kind of goes up and then comes down. And this is pretty acceptable. In rare event estimation, they're thrilled if they can get the standard deviation of the rare event probability to be on the same order of magnitude as the thing you're trying to estimate. That would be just fine. And these are, yeah, so these are pretty small. You don't really need 10 to the minus 40, but, no. But the fact that you can get 10 to the minus 40 might make you feel more confident that if you needed 10 to the minus 12, you could get it. Or 10 to the minus, 5 times 10 to the minus 8 is what they're gunning for, and this seems to be, maybe it's even overbuilt compared to what we need. Let's see. I have a couple examples here. These are cases where we knew what the true p-value was because the sample size was small. This is the plain volume estimator. This is the one that I told you that I liked. On this axis is the ratio of the true p-value, the estimate divided by the truth, and the estimate flops around quite a bit compared to the truth on the small sample size. The saddle point approximation is kind of the best thing out there theoretically, but it doesn't come with any estimate of its own error. We get a root mean squared error. You don't have that. Also, the saddle point estimate tends to underestimate, so it tends to be a little bit too optimistic. Most of the time, it's too small. For normal data, what I showed you was for normal data, it wasn't that accurate. We tried lots of other distributions that's kind of the same. And then a surprise, Hera also ran it on some real gene sets from a real Parkinson's disease study, and then p-hat 2 seemed to beat the saddle point on the real gene sets. In normally distributed data, it wasn't really beating it by much, but in the real data, it seemed to do better. And we have no understanding why real data would favor us. Maybe the next real data set, maybe that's just the lucky disease for us. Some other disease that's different. So what can you do? Well, you could do all the permutations. Well, it's exact, but it's too expensive. You could do Monte Carlo. It's pretty much exact, but it's still too expensive to get a small p. Saddle point approximation, it does give you relative error control. That's known theoretically, but you don't get any idea whether your estimate is good. You don't get an error estimate. And sometimes it seems to be biased down. This simple p-hat, that's basically what the t-test will give you, and it's not very accurate. This p-hat 2, the new thing, it gives you good relative error. We don't get an end-to-end probability statement. We get a variance estimate for our p-hat. And we want more, but we don't have one. And there's a third thing that's a little bit more conservative, but I think this is the best one. Okay, so what's next? Well, Hera's dissertation, she looked at the quadratic case. I told you Ackerman and Strimmer found two things that win. The second one was square the t statistics, then add them up. And that requires some very complicated methods. There's some other connections to various things that in the literature. There's something called rotation tests that look a lot like Model 1, the volume. Okay, and challenges, I told the quasi-Monte Carlo people we want L infinity, L2 is not going to do it for us. And the quadratic case, you have to deal with quadratic spirals and caps. Get me all the x's where x transpose qx is above the threshold. Those are funny looking sets on the unit sphere, and they have odd boundaries, and it's hard to count the points in them. Okay, I have a lot of, I thank my co-authors. John Robinson gave me a lot of help about saddle point approximations. Jessica Larson was at Genentech when I was there. We had a good time talking to her and the other Genentech people. I have financial support. I want to thank Paul Constantine for inviting me here, and thank everybody for listening so far.
Lots of time for questions. Any questions for Professor Owen?
Just a basic question. So one of the things we're trying to do is not just get the accuracy, but speed it up. What's the general computation time or something like this? I didn't see this slide.
Oh. Well, I had M0 and M1. And M0 was like how many people were without Parkinson's. M1 was the number with. The computation for the, it depends whether you want to calculate the root mean squared error. The root mean squared error was dominated by about M0 cubed integrals that you had to do. So you have to do like these integrals to get the incomplete beta business. If you didn't want to calculate that, then it's basically M0 things that you sum up, some combinatorial stuff. So it's really pretty fast. But if you want the variance estimate, then you've got to do M cubed. There's an M4th step in there, but it's not. That's just getting coefficients. It's M cubed integrals, and that's the dominant time. And it wasn't that expensive.
So related, what are some of the M0s that you might see in practice for a real genome-wide association test?
Well, so in this talk, I was switching a little bit between genome-wide association tests and microarray tests. So in the microarray test, you have a gene set. In the genome, they really can't afford permutations at all. So hardly anybody's doing permutations because you have that 5 times 10 to the minus 8 thing. If we're lucky, people will take this up and actually start doing, SNP sets on GWAS. On the Parkinson's data, the sample sizes will maybe like 50 people total, nearly equal numbers in the two groups. And we had 3 different studies that we looked at. So they're pretty smallish samples. 6,000, they tested like 6,300 different gene sets on maybe 80 people. Yeah.
I'm curious as to where the 5 times 10 to the minus 8 comes from. Is that from a von Neumann correction?
Yeah, it's a social number. So
What does that mean?
so
What's a social number?
Well, the scientists or the literature sort of agreed that if you test 1 million things and you want a 1 in 20 p-value after doing 1 million tests, then you need 5 times 10 to the minus 8. But they don't really have exactly 1 million SNPs. And, it's clear that 0.05 isn't the right number for that. It's not so clear that there is a right number.
Any other questions? I've got one more. If your p-value is 10 to the minus 40, do you now get to say anything about causality?
No.
Nothing at all.
Well,
what if it's 0?
That's still not causal. I mean, you can have a spurious correlation. There could still be a third factor that makes both things move together. Or the causality direction could be the opposite of the one you think. Yeah. Or your model could just be wrong too. So there's a lot that can go wrong on the way from a p-value to a conclusion. Yeah.
I have one more question. Nobody else has any others. So you sort of mentioned you hope that places like Genentech would take this up and use it for something like a genome-wide association study. How do you make that happen? Do you have to quit your job?
I'm not really good at making that happen.
Okay.
I wish. But I think Hera wrote an R package for it. And
so
then,
software is one avenue to do that.
Software, and then you think, well, of course, people avidly read the entire literature until they find your paper and realize you solved their problem.
Right.
Or you go to departments around the country to give talks, or I talked about this at NCQMC. So I haven't got really great ideas on how you get something out there so that people actually do it.
Anybody else? Yeah.
You said you usually test for gene sets rather than individual genes.
Yeah.
How do those sets show? Math or scientific?
Oh, so there are 2 main things. There's the Go group, which is gene ontology, and they'll have a tree structure. So somebody decides that all of the genes in your body, or not actually even in a worm's body, belong in some tree structure. And there are 3 different tree structures. One is by function, one is by structure, and maybe it's by location. And then there's another group, KEG, from Kyoto. And so they've clustered the genes according to something that makes sense biologically. And there's all of your inputs in bioinformatics are kind of noisy. It's not clear that one of those gene sets is like the real gene set, or the label on it. It'll have some label that might not be 100% perfect fit to the genes that are in it or not in it. So they keep revising the gene sets too.
Could you pick those out?
Pardon me?
Could you pick those out if you what you get an appropriate gene set?
So you mean, like in a paper, there would be a biologist on the paper who would then say something about what the gene set you found might mean. So on a paper with Jessica Larson, I had a previous method, and we would find various gene sets, and then she kind of knew that some of them had already been implicated in Parkinson's, some of them had been implicated in something that was known to be related to Parkinson's. And I think you're always hoping to find something that somebody found before, and then you're also hoping to find something you didn't find before. And I guess you like them both. But either way, you win. Yeah.
All right, let's thank Professor Owen. Yep. Almost done. I'll just get it. Okay. Say that our next colloquium is 2 weeks from today. Stefan Wild from Argonne National Lab, the computational mathematician, will be here to talk to us. One other thing, so we're going to stick around here for the next hour. If you would like to stay around and talk about more technical things and have more technical questions, that's what we'll be doing. Also, there's still a couple more spots open for dinner. If you'd like to join us for dinner, we have a reservation at a Bay House, so let me know. Otherwise, thank you all for coming to Colloquium. We'll see you in 2 weeks.